Look at these two systems. On the left, a computer choking to death, its CPU fans screaming before ultimately throwing a fatal error. On the right, the exact same machine finishing its identical task in a fraction of a second. Both systems are running identical hardware. The only difference is the invisible architecture of the code they were handed. Developers often write functions that call themselves, a technique known as recursion. When calculating a sequence like Fibonacci, a recursive algorithm looks incredibly elegant, reducing complex math into just 2 or 3 lines of code. But that conciseness hides a mechanical flaw. A plain recursive function has absolutely no memory. It doesn't know what it did 1 second ago. When code is perfectly clean but entirely forgetful, it becomes a trap for your hardware. Elegance without memory forces a processor to work itself into the ground. To compute the 40th Fibonacci number, the algorithm splits into thousands of tasks. Without memory, it redundantly calculates the 38th number on both the left and right. This exponential, O of 2 to the n complexity, doubles calculations at every step, rapidly escaping the physical limits of the processor. The computer didn't freeze because the arithmetic was difficult. It crashed because the algorithm was duplicating its own effort millions of times over. To stop the processor from repeating itself, we have to give the algorithm a memory. This requires a strict economic exchange. We are going to spend physical memory space, our system's RAM, to purchase back CPU cycles. But we can't just throw data into a pile. Searching through a disorganized list for a past answer takes so long that the processor might as well just do the math again. The lookup mechanism has to be instantaneous. In languages like C++, we built this using a standard unordered map. It uses a math formula called a hash function, taking our input, like the number 38, and translating it directly into the exact memory address where the answer lives. This gives us an average time complexity of O of 1. Whether the map holds 10 items or 10 million, the key drops straight into the correct bucket, skipping the search entirely. Sacrificing a few kilobytes of RAM to build a constant time hash map is the most profitable resource trade you can make in software engineering. We deploy this map using a technique called memoization. We mandate a strict new rule. Before the algorithm is allowed to do any math, it must query the cache. If the answer isn't there, we hit a cache miss. The algorithm is forced to do the hard work, but before it hands the answer back, it permanently records the result in the map. Let's run the execution path again. The left side of our tree works its way down, calculates a specific node, and commits that value into the central storage box. Then, the right side attempts the exact same calculation, but this time the cache instantly outputs the answer. The algorithm stops dead, completely bypassing the massive, sprawling branch of work that used to exist below it. From here, a chain reaction takes over. Every time the algorithm tries to repeat a task, the cache fires back the answer, severing branch after branch after branch. The hash map acts as a computational firewall. It stops an exponential explosion in its tracks by forcing the system to read a database instead of running a redundant calculation. With redundancy severed, the infinitely branching web collapses into a straightforward vertical line. This chart shows the performance gain. We've forced a catastrophic exponential curve into a flat, linear execution path. A process taking years now finishes in milliseconds. But this technique has strict boundaries. Memoization only works for pure functions, where identical inputs guarantee identical outputs, and problems that actually contain overlapping subproblems. Even then, the call stack, the physical memory keeping track of the recursion, has a depth limit. If an input is massive or controlled by a malicious user, the stack will still overflow. In those cases, you abandon recursion entirely and use a bottom-up approach known as tabulation. Recognizing when to use a cache is the exact threshold where dangerous, naive code evolves into the highly optimized discipline of dynamic programming. Mastering the space-time trade-off means you stop fighting the limitations of your physical hardware and start exploiting them to your advantage. Explore the C++ unordered map implementation used in this video by visiting the GitHub repository linked below. Pull down the code and trace the memory allocation for yourself. Optimization is an ongoing discipline of making your code respect the silicon it runs on. Next time,